Ich glaube, sie holt uns. Good afternoon and a very warm welcome to the heart of Berlin. It's lovely to have you tuned in online and present on site for what is promising to be a very compelling afternoon hosted by the German Federal Ministry of Research, Technology and Space. So welcome everybody for the Quantum Future Award 2025. It's great to have you. My name is Helena Felixberger. I'm a communication specialist, a conference interpreter, and a multilingual moderator. And it's my absolute pleasure and a privilege to be with you this afternoon and guide you through this 8th edition of this very special event that is coming to you live from the ministry. Now, quantum technology really is driving some of the most exciting breakthroughs of the 21st century. It surely is changing the way we understand the universe. And it certainly is challenging the way we perceive reality. Now, in the quantum world, light can behave as both as a wave or as a particle. Electrons can be at multiple spaces at the same time, and particles can be mysteriously linked no matter how far apart. Now, you are all here because you know this, and you're all here because you also understand that quantum technology is not just a field of study. It is the very fabric of our technological future. And today, we are here to celebrate the people who are weaving that fabric. Now, the Quantum Future Award is proudly presented by the German Ministry of Research, Technology and Space, and it is dedicated to acknowledge great minds. young quantum future professionals who are turning complex theory into real-world application-oriented quantum technology. And as it is, this year is the UN's International Year of Quantum, there's also like a global call coinciding with our commitment here in Germany. So it's like those two particles I mentioned before, mysteriously linked no matter how far apart. Now, over the next couple of hours, we will witness 10 of the brightest young scientists in Germany present their work, their groundbreaking work, 5 from the master's category and 5 from the PhD category. They're all sitting here in our audience. Maybe we can switch the camera a little bit. There they are, expectant, excited, and of course confident. Maybe you could give us a little sign with your thumbs. How do you feel? All thumbs up. Great. I knew you're going to be great. I mean, look at you. But before we proceed, we must pay tribute to the expert jury who will have the unenviable task of deciding our winners. They have spent countless hours poring over the full theses, and they have the tough job of judging the final pitches. Ladies and gentlemen, here come 3 members of the jury of the Quantum Future Award 2025. Let me introduce them. Now, first up, representing the very best of cross-border scientific collaboration, she is a bridge professor between the Karlsruhe Institute of Technology and the University of Strasbourg, focusing on quantum technologies, and she is a real powerhouse in theoretical physics. Welcome, Professor Dr. Anja Mittelmann.
Welcome.
Next, representing the new guard of quantum professors, he is building and expanding the Institute for Quantum-Inspired and Quantum Optimization at the Hamburg University of Technology, and his work focuses on various aspects of quantum computing. He's a true pioneer. Welcome, Professor Dr. Martin Kliesch. And finally, representing the vital link between groundbreaking research and industrial application, he is the Senior Director for Funding, Projects and Coordination at the global tech giant Infineon Technologies. We are very grateful that he was able to step in for his colleague, Dr. Sebastian Luber, who did the initial assessment of all theses. So glad that you made it here today. Please welcome Dr. Christian Meine. Now, a quick question. Why do you think is the Quantum Future Award so important for fostering quantum future professionals? Professor Kliesch, maybe if I can ask you.
So, yeah, thanks for the question. Quantum technology is a very rapidly expanding field. Like, we have seen so much new research coming out in the last years, and it's really difficult to keep track of all the wonderful research. So prizes like this are a great opportunity to really to point out the highlights of what has happened in the last year. And I had a lot of fun, enjoyed it a lot to read the thesis.
Thank you so much, Professor Kliesch. Now, Professor Mittelmann, what did you find most striking or maybe even most challenging in assessing the submitted works?
Oh, there were a lot of pages to read. One challenge, to find the time. No, they were wonderful theses, and I think they're also matching the Quantum Future Award in scientific quality and the application side and all this. So judging this, ranking this, measuring this, is pretty tough, and that I think was the biggest challenge. But it was also fun to read your thesis, so thank you for having the chance to do it.
Well, the biggest challenge is yet to come, Professor Mittelmann. So, Dr. Meine, your role is to evaluate the commercial viability of research. What is central for that?
Well, first of
of course, the step from the university laboratory into mass production, or the possibility to strive all these things into mass production, and under the circumstances or on the boundary conditions of mass production in the front-end fab for, like Infineon, for example, where we have, of course, a lot of other things to mention and to take care for. Then you have the possibility in the laboratory at the university, of course.
Thank you very much, Dr. Meiner. Now, before we unleash the power of the 10 final pitches, those of you who paid close attention will have noticed that there's one member of the jury missing. Well, that is because she deserves special recognition, there we go, for being our host today. She is Director General of the Department of Technological Sovereignty and Innovation here at the Ministry of Research, Technology and Space, and she is the driving force behind the Quantum Future Professional Agenda and, of course, the award. Here comes Dr. Alexandra Gwynn Pitts. Welcome. The stage is yours. There you go.
Thank you. So, dear and distinguished guests in this room, and all of you who are online, members of the jury, esteemed finalists. It is my great pleasure to welcome all of you to the presentation of the ceremony for the Quantum Future Award 2025 at our Federal Ministry for Research, Technology and Space in Berlin. Although I think it's the 8th time that we are rewarding this, it is still a very special year, and you just mentioned it. It's the United Nations International Year of Quantum Science and Technology. And throughout this year, I have been to several quantum events, but I believe finally today I will hopefully have understood the quantum mystery and get some explanations just in time before this year is over. So I'm just trying to set the expectation level a little bit higher. A few weeks ago, and somebody just mentioned, our event in Berlin launched the High-Tech Agenda Germany, which I have here with me, which provided major impetus for enhancing Germany's innovative strength in pioneering 6 key technologies, and one of them obviously includes quantum technologies. And this brings us to today's topic. You, the finalists, are among the young minds who already shape this future. You've decided to focus your studies or your research in a field that will not only be essential, which is already essential in our technological sovereignty, and which has enormous potential for applications in medicine, in energy, in logistics, and I'm sure we will hear more about that. You, the young researchers and students, know best how quantum technologies fundamentally change our way of handling data, materials and computer power. Probably you again became aware of a disruptive dimension of quantum technology applications during yesterday's network at the Ferdinand Braun Institute, and I'm very happy that you're having a couple of days here in Berlin, and I guess you brought the sun because yesterday it was a really rainy year. Much is still to be done as we move forward towards broader applications of quantum technologies. For this, we need a new generation of talented people like you, people with courage, creativity, experience, and the ability, as well as the willingness, to think out of the box. That's why this summer, we, at our ministry, published our program entitled Quantum Future Professionals, which is part of the High-Tech Agenda Germany. You know, this is something I have in my pocket since a couple of months, every day with me. We want to encourage, our Quantum Future Professionals program has, among others, a funding call that covers the entire educational and professional career from school to university and then to industry, as we just heard, as well as politics. To us, it's also important to understand the mystery of quantum. Our aim is to identify requirements, provide educational pathways, increase program visibility, and capitalize on the talent pool to increase Germany's international attractiveness in the global skills competition. The award we are presenting today is a major instrument for career advancement, as it gives visibility not only to the technology, but to the talents that drive this technology for the good and our well-being. As I said, this is the 8th time that the Quantum Future Award is honoring outstanding master's and doctoral theses, which combine scientific depth together with an application orientation. As all the finalists here have already prevailed against strong competitors, which deserves, I think, a round of applause that you're here already. Congratulations. You are now going to present your projects in only 3 minutes using only one slide. And what would be really a challenge to me is probably a fun task for you. So I'm really looking forward. And I also want to share my special thanks to our jury for carefully reviewing all the projects submitted and giving us your time. As you said, there were many pages. The members from academia were already presented, Professor Anja Mettelmann and Professor Martin Kliesch, as well as Christian Menjan. Thank you very much for stepping in. I'm now looking forward to the pitches and finally understand the mystery of quantum, and I wish to all the finalists a lot of success, and we will meet with some of you back later up here. Thank you very much.
Thank you very much for your words, Dr. Peetz. Yes, it is so important to make talents visible. And, well, you've set the challenge. The challenge is on now, and it's not an easy one, I can tell you. Right. It's time for the main event. This is where the rubber meets the road, or maybe where the qubit meets the quantum processor, if we can do that. Let's talk about first what the finalists are competing for. Of course, the Quantum Future Award consists also of a significant prize. It's not only fame, it's not only recognition or visibility, there is significant prizes for all the winners. Now, the second place winner in each category will receive a study trip valued at 4,000 euros, and the first place winners of each category will receive a study trip valued at a magnificent 6,000 euros and will get to take this beautiful glass trophy home. If one's missing, you know where it is. There you go. No, I will not take it. I don't deserve it. Now, there also will be an audience award for the person whose pitch you liked best because it was the most compelling and the most engaging and the most clearly communicated, which also is essential. And this will be a further training opportunity in science communication, so they are assisted in sharing their brilliance with the world, because that's also important. Also marketing, I'm afraid, is important even for scientists and researchers. So, for those joining us in the live stream and for everybody here present, that means that you also have a very decisive job to fulfill. As soon as the pitches are complete, the online voting for the Audience Award will start. So listen closely. Maybe it's a good idea to have a notepad ready or your mobile and key in a couple of notes so you remember who you liked best. All right then, the jury is sitting in the very first row. That's very good because they will be watching closely. They are not allowed to miss anything. And we will start with the masters category. These 5 researchers have tackled some truly immense challenges in their theses. Let's see what they've got. Our first finalist has been looking at the very real problem of noise in quantum computing. That's a bit like trying to have a serious conversation right next to a jet engine. In her thesis, she characterized 3 variational quantum algorithms in terms of their scalability in the presence of noise. Highly relevant work, so please welcome from the Technical University Munich, Adelina Berligea. Welcome.
Thank you.
All good with you, Adelina?
Yes.
All right, time's running.
Quantum computers will change the world. At least that's what the headlines promise. And this promise has already triggered billions in global investment, much of it focused on building the ultimate quantum hardware. But there's a critical question we don't ask often enough. Even if we had a perfect quantum computer today, would it actually be useful? Of course, we have many ideas for applications, but the algorithms that would make these machines solve real-world problems are actually still rare. In my thesis, I looked at a very popular candidate for achieving this promise: variational quantum algorithms. They're hybrid methods that combine both quantum and classical computers. You can think of them as a special kind of race car. It has a classical driver who tries to find the fastest path to the finish line, but instead of a normal map, it uses a powerful quantum navigation system capable of exploring many possible routes at once. In theory, this combination looked unbeatable, and it quickly became the leading method to tackle a whole range of hard optimization problems. But there's a catch. To know where to steer, the driver has to look at the map by measuring the quantum system. But because these measurements are statistical, each one only gives an estimate. This built-in uncertainty is what I call measurement noise. It's as if our driver has to navigate using a handful of blurry snapshots instead of a clear GPS signal. So I asked, what happens when the race gets longer and the map gets blurrier? What I found was this clear scalability barrier. For small, simple problems, the driver does just fine. But as we scale to useful sizes, the level of noise the driver can handle collapses. The map gets exponentially fuzzier, and beyond this critical point, our driver effectively becomes blind. Now, to keep the car on track, it would need an astronomical number of measurements. In other words, the race becomes so expensive that you'd have been faster just walking. Instead of achieving quantum advantage, we achieved a disadvantage. No, this may sound discouraging, but it's not. Science moves forward not only by building faster cars, but by understanding which ones cannot finish the race. By identifying these dead ends, we can focus our effort where real progress lies. My work helped to map those boundaries. It tells us this race car can't win, but now we know why. And with that knowledge, we can start designing the next generation of quantum algorithms that can truly handle the road ahead, with more powerful engines, smarter drivers, and clearer maps. Algorithms that can really change the world. Thank you.
Spot on, Adelina. So a strong start, you know, she started the race, really. That's what she did. Be the map clear or foggy. Well done here. So next up, we have a finalist whose thesis on cryogenic etching is about optimizing the growth of superconducting qubits to reduce their size, which is vital for scaling up these systems. He's also from the Technical University of Munich. Please welcome Christian Gnant. Welcome, Christian.
Thank you.
You ready?
Ready.
Okay, time's running.
Thank you for the kind introduction and welcome everyone. Accelerated design of batteries. accurate molecular simulation for drug discovery, efficient optimization for manufacturing. Quantum computing promises breakthroughs across multiple industries. Given the time that has passed since Feynman's proposal in the 80s and the profound impact that is envisioned, building a quantum computer is clearly a hard task. So the big question becomes, what are we missing? Just like classical computing processors, a quantum processor is composited of many smaller computing units, known as qubits. For wide-scale industry adoption, it is estimated that we need a few million of these, all of which must be operated under quantum conditions. For superconducting quantum processors, that means cooling them to just a few millikelvin above absolute zero inside a refrigerator, with a diameter of at most half a meter. To put this into terms of qubit count, such a system will only be able to host a few thousands of these at its limit, with a standard qubit occupying about 1 square millimeter of circuit area. This reveals one answer to our big question. We are missing 3 orders of magnitude in physical space for our practical quantum computer. To overcome this limit, let's reconsider the footprint of a superconducting qubit. It contains only 2 components, a nonlinear inductor and a superconducting capacitor. And a quick look at the micrograph shows us that it's the capacitor that dominates its size. Here's where my master thesis comes in. The team at the Waldner Meister Institute and I have developed a novel fabrication process that replaces the bulky planar capacitor with a space-efficient 3D structure. The result? An ultra-compact superconducting qubit that is up to 2 orders of magnitude smaller than its planar twin, while maintaining comparable performance and surpassing state-of-the-art devices at its size. The core fabrication method that carves out the silicon fin to form the capacitor dielectric has been developed in 1988. Our contribution is identifying it as a suitable process and adapting it, a prime example of how this platform can benefit from decades of semiconductor research. With the support of the Quantum Future Award, I aim to conduct research days at international specialized fabrication laboratories that explore such synergies between microfabrication methods and quantum hardware and integrate these into our processes. The demonstrated integration of silicon fin technology presents a milestone for large-scale quantum processors. And with each additional milestone, we are getting closer to building the next paradigm of computing technology right here in Germany. Thank you for your attention.
Thank you very much. Christian Gnand. And in case you're taking notes, Adelina Berligia is the race car driver we had before. Yes, you were even 1 second ahead, so that's for less bulk and ultra-compact design, even in your presentation. Well done there. Now, our third finalist has explored the domain of quantum communication. His work demonstrated entanglement via a long-distance fiber in Munich, through Munich, which is key for future quantum networks and distributed quantum computing architectures. And as we said, through Munich, of course, this person is also from the Technical University of Munich. It's Marvin Scholz. Welcome.
Thank you very much.
So, Marvin, you're all set and ready? Time's ticking.
The information age, especially the classical internet, has been one, if not the most technological advances in the past decades. This is demonstrated by the fact that 97% of young Europeans use the internet daily. And nowadays, researchers such as myself are working on a second generation of the internet, the so-called quantum internet, based on the principles of quantum physics. And just like the classical internet, a quantum internet would consist of many different nodes, which could be you, the user. But now you would be using a quantum computer in order to access this internet. Now these nodes are connected through channels, which are just your ordinary glass fibers that you already know that have been installed to your homes. And information would be exchanged between these nodes through these channels using single photons, which is the smallest part of light that you can have. And now this future quantum internet is interesting because it has many different applications, such as quantum computing, where if you connect multiple different smaller quantum computers, you can build a more powerful, bigger quantum computer. It also has applications in secure communication, where you can have provably secure communication between multiple parties based on the principles of quantum physics. And finally, by entangling all these different nodes within the internet, you can sense more precisely than classically possible. Now, speaking of entanglement, entanglement is really the key resource of this future quantum internet. But it is very fragile, because it is a shared property of at least 2 nodes. And we tried to do exactly that. So in Munich, we tried to entangle a single atom within Munich and a single atom within Garching, connected through glass fibers. And now my contributions to this project included the characterization of the glass fiber, where I found the glass fiber that was most suitable as a quantum channel. Moreover, I built a filter cavity setup in order to filter out the background light. And finally, and most importantly, as the main result of my master's thesis, I demonstrated atom-photon entanglement, which can be seen from this graph. What I extracted was an entanglement fidelity of 0.81, which is very close to the ideal value of 1, thereby proving entanglement. And so this is a very exciting step towards a future quantum internet, and we hope to continue this research with showing different applications. Thank you.
Thank you very much. That was Marvin Scholz, the fastest so far. 17 seconds, still on the plate, super easy. And he was connecting nodes for the future quantum internet. Moving on, our 4th finalist has been leveraging numerical simulations to realize advancements in waveguide designs. And he has even filed a patent based on his work. Now that's application relevance right there. From the Friedrich Schiller University in Jena and Fraunhofer IOF, please welcome warmly Trevor Vrchkovnik.
Thank you.
All right, Trevor, you are ready. Born ready he was. Time's ticking.
Quantum encryption and computing schemes are a matter of national security and are needed in the future for secure data transfers. As well, I'm sure we're all looking forward to the day when we can touch, feel, and use quantum technologies in our everyday lives. Unfortunately, most devices currently look like the entangled photon source former Chancellor Merkel's holding. They're big, heavy devices that cost a fortune just to produce a single unit, and they're not always practical. I mean, I'm sure some people wish that they had the ability to have quantum encryption embedded directly in their cell phones. For this, we need to turn to integrated circuits and produce these devices out of waveguides on chips. These are smaller and cheaper to produce, meaning that they're the true future for practical applications. Other people who have tried to integrate quantum sources have relied on complex engineering schemes, meaning they're not so practical for future scalability to mass production. In my thesis, I looked at ways that we can change the design of these waveguides and exploit the natural symmetries of crystals to produce these devices in simple waveguides that are just straight with a rectangular cross-section. I did this by first building a simulation tool based on the coupled mode theory, which can simulate second-order nonlinearities like second harmonic generation or spontaneous parametric downconversion. Unlike commercial softwares, my tool is fully capable of handling the complete nonlinear tensor as well as any anisotropies in the crystal, meaning that we have more freedom in our waveguide designs. As well, the efficiency of my tool means that we can do vast parameter space sweeps, sweeping over thousands of different geometries to find those which are most efficient. Because we can see the eigenmodes involved in the processes, I can then further refine my geometries to be able to maximize the mode overlap between these modes, thereby creating state-of-the-art efficiencies, but in devices which are much simpler to build. I then looked at some specific quantum applications, like the production of polarization entanglement photon pairs. By looking at the nonlinear tensor, I was able to identify the elements that are most essential for SPDC in these waveguides, and then classify every single crystal class based on their suitability. Two materials, barium titanate and lithium niobate, were of particular interest because they looked quite promising for this work. Through various simulations using different input schemes, I was able to show that waveguides made from these two materials of specific dimensions are fully capable of Bell state generation, meaning that they can produce maximally entangled photon pairs in devices smaller than a human hair, and orders of magnitude better than what we currently have. Now, the versatility of my tool also means that in the future, we could try to optimize for other quantum states if needed, such as perhaps squeeze states. Overall, these waveguides are the first of its kind to produce integrated light sources without the need for periodic polling or Bragg reflection structures. Because of this, they're more reproducible, cheaper, and smaller than any other quantum light sources available, making this work absolutely essential for us to one day have wafer-scale production of quantum technologies and bring quantum encryption to us all. Thank you.
Thank you very much. This was Trevor Vrutkovnik. All the best of luck with your patent. And to round off the master's category, our fifth master's finalist has been investigating the security of quantum key distribution systems against sideband attacks, showing provable ways to security. From the Technical University of Berlin and Fraunhofer HHI, please welcome Jerome Wiesemann. Welcome, Jerome.
Thank you.
Ready and set, so we say time's ticking.
Quantum computing is often presented as a technology full of potential. And while this is true, the security implications often receive far less attention in the public discussion. Yet some of our most critical financial assets, or government networks, or health data, are currently being protected by encryption schemes which can be broken by quantum algorithms. This means that to protect our digital sovereignty, we need to explore new solutions. And quantum key distribution is one of the most promising solutions. It relies on fundamental quantum laws to establish a provably secure key that can be used to encrypt data or privately communicate in a way that cannot be broken by quantum computers or any future technology. QKD is one of the most mature technologies of the second quantum revolution, with Germany and Europe currently building some of the largest networks in the world. However, today there is a gap between the theory used to show QKD is secure and the devices we built. And this gap can be exploited by an adversary, making QKD systems vulnerable to attacks which compromise security. In my thesis, I've specifically focused on closing this gap by taking a dual approach. On the theory side, I developed a new security proof, providing rigorous theoretical foundations and allowing us to identify where real devices deviate from idealized models. On the practical side, I identified vulnerabilities, implemented countermeasures, and provably protected an in-house QKD system against some of the most critical attacks. Just like for classical cybersecurity, the certification is essential to successfully commercialize QKD. And penetration testing, that is, intentionally trying to hack the system, is an important part of certification to make sure the systems are really secure in practice. In my thesis, I showed that today's QKD systems can be exploited with current technology by implementing two of the most critical attacks on QKD. And the methods we developed in my thesis are now being integrated into the blueprint for the very first European certification lab, which is currently under construction. We provide concrete tools, both theoretical and experimental, to make sure that QKD is not only secure in theory, but also secure, testable, and certifiable in practice. To protect our digital infrastructure, we need to explore quantum-safe solutions. And I believe it is crucial that we develop a good and deep understanding of the security aspects involved. My work contributes towards this goal, to help ensure our data and communications remain secure as quantum technologies move from the lab into real-world applications. Thank you.
Thank you very much. That was Jerome Wiesemann, for everybody who's taking notes, who convinced us in just 2.5 minutes. Well done here. And thank you for your efforts to protect our digital sovereignty. So that was the master's category. 5 exceptional pieces of work, 5 different approaches. And now we move on to the PhD category. Now, these are the doctors, these are the seasoned researchers, and their work certainly is pushing the boundaries of what we thought was possible. Our very first PhD finalist has realized a robust and fast setup for quantum holography, a technique for quantum imaging with undetected photons. It sounds like something straight from the holodeck, but it is indeed very real. And she comes from the Friedrich Schiller University, Jena, and her name is Dr. Marta Gilabert-Basset. Welcome.
Thank you.
You're ready, set, go? Okay.
I'm ready.
Go.
Hi, everyone, and thank you for the introduction. So light carries a lot of information about the world around us, but our eyes or even regular cameras are only detecting one very small portion of the spectra, the visible range. For example, in this picture right there, what you see is how proteins reorganize in the brain during a stroke. And that information is stored in the infrared, which is invisible to our eyes, but luckily not to infrared detectors. Now the problem is that ideally we want to illuminate the sample with very low light levels to not damage it. And under these low light conditions, infrared detectors are noisy and not as efficient as visible detectors. And that often means poor image quality. And that's a general problem. There are many applications where light outside the visible range is needed and at very low light levels. For example, the UV light to observe cell division processes, or the infrared to monitor the brain, but also to check on the retina during an eye exam. So how can we improve the image quality for all these cases? Well, why not take the UV or infrared light to illuminate the sample while using the visible light to optimize the detection? Well, that's actually what quantum imaging with undetected light allows us to do. And here's how. We place a nonlinear crystal inside an interferometer, and we pump it with a laser beam to generate pairs of correlated photons that can have different wavelengths, one in the infrared and the other one in the visible. So using the quantum interference effects and the spatial correlations between these photons, we can achieve to get an image of the object by using only the visible light. Or in other words, we can detect what the infrared light saw, but without ever detecting the infrared itself. So this is a very powerful technique. But to be ready for real-world applications, we also need to take care of some more practical aspects. So in my thesis, I tackled some of these challenges by building one of the first portable quantum imaging systems that is able to image at video rates. And I also identified the more, how to stabilize the more sensitive components to have robust systems that can work even outside ideal lab conditions. Now, there's another very important feature for for imaging systems in general, which is resolution. That's why in the second part of my work, I focused on studying to optimize the correlations between these photons to enhance the image resolution for specific applications. And so I hope I could convince you of the great potential of quantum imaging with undetected light, and that my work contributed to bring it one step closer to practical use. Thank you.
Thank you so much for those taking notes. That was Dr. Marta Gilabert-Basset on the enhancements of image quality, of image resolution. Thank you very much. Next up, we have a finalist who is focused on enabling technology for quantum sensors. His thesis demonstrates miniaturized radio frequency electronics for the manipulation of NV centers. He comes from the University of Stuttgart. Please welcome Dr. Hadi Lotfi.
Thank you for the introduction.
So you have the mic, you have what it takes, and the time's ticking.
Quantum sensors are already revolutionizing science, with application from measuring temperature and pressure to exploring mobility and materials at nanoscales. But today, they are trapped in lab, bulky, complex, expensive, and even hard to scale. A single quantum magnetometer can cost over 100,000 euros, relying on massive rack-mounts equipments that could take up an entire lab bench. Despite their incredible potential, quantum sensors are not yet part of our everyday life. My vision was bold. What if all of the microwave quantum hardware could fit on a single chip? Imagine controlling the quantum spin state using the same type of circuits that power your smartphone. Suddenly, quantum sensors could become portable, affordable, and scalable, ready for real-world application across both science and industry. Together with Envision, Robert Bosch, Helmholtz Institute, and KIT University, we built the world's first diamond-based quantum magnetometer using chip-based microwave source. We designed, fabricated, and measured flexible platforms tailored for different frequencies, magnetic field, and sensitivity volume using driver and readout chips. One of our microsystems achieves sub-nanotesla resolution, enabling nanoscale NMR for cell diagnostic and high-throughput drug screening. Using custom glass process with PCB-based microcoil and application-specific integrated circuits, our system replaces 100,000 euros commercial signal generators, while it can generate a variable microwave magnetic field suitable for modulation of the quantum spin state of NV center inside a diamond slab that is placed on top of the microcoil. Using this method, we can enhance the sensitivity of the AC and DC magnetic field and improve the sensitivity volume compared to prior arts. This method also can reduce the cost, size, and energy use, and it is now compact, efficient, and scalable, a quantum sensor on a chip. This technology has reached TRL 5 and is now advancing toward TRL 6, with the first commercial product expected soon from Envision. Part of this work so far has been published in over 13 journals and conferences papers, laying the foundation for a new class of quantum RFIC that could merge quantum physics with semiconductor technology. And this is the future we are creating: quantum intelligence integrated directly into silicon, small enough to hold in your hand and yet sensitive enough to explore the quantum world. Thank you.
Thank you very much. Also, he was very, very fast, small enough to hold in a hand, really. That was Dr. Hadi Lotfi. Thank you. And now we have the third PhD finalist. He has developed and realized a new class of quantum light sources. His thesis is highly relevant for quantum communications and photonic quantum computing, and he comes from the Technical University of Berlin. Please welcome Dr. Lukas Rickert.
Thank you.
Okay, ready, set, go.
As we've already heard today a little bit, if we want quantum technology to move into real-world applications, we need quantum hardware that is performant, practical, and ideally scalable. Integrated photonic quantum technologies using solid-state systems might be able to tick all three of these boxes and still be manufacturable on the same scale that we know from our current chip technology. In my PhD thesis, I've developed a new class of solid-state emitters that are practical and are still capable of producing high-quality photon states ready to use for quantum information protocols. The key component is a semiconductor quantum dot, an artificial atom in the solid state, which is deterministically embedded in an on-chip cavity which is attached to a single-mode fiber, giving us practical photon states directly usable in fiber and ready for applications. I've employed a fabrication process that ensures that the cavity is perfectly matching the emitter, which drastically reduces its decay properties, in the sense that we have ultra-fast emitters that overcome performance challenges that have been a problem so far. For example, the ultra-fast decay leads to nearly identical photon emission, which negates, or which is helpful because it negates the noise that is imposed by the surrounding semiconductor. We could also show that these properties prevail for temperatures which are now an order of magnitude higher and are reachable with compact cryocoolers, which allows us to put these devices into compact modules, readily moving it outside of the lab. And last but not least, we could show that with an ultra-fast decay, we also gain the property to drive these systems at much higher repetition rates, which will boost the communication rate of quantum communication experiments in the future by more than an order of magnitude. We could also show that these devices have an actual use in applications already. Me and my colleagues conducted an experiment where we showed that we can gain an actual quantum advantage in a quantum cryptographic primitive beyond QKD, where we can show that such a chip device can beat classical devices. And last but not least, I had the great pleasure to contribute with one of these chips for the award-winning outreach project Quantur, where, we've already heard it, in the International Year of Quantum, a lot of outreach was created, and our contribution was that we let this chip travel over the whole year to more than a dozen different locations in Europe, generating outreach, inspiring people, sharing our fascination with quantum science, and hopefully already inspiring the next generation of quantum scientists to join us in this task to move this technology into the real world. Thank you very much.
Thank you very much. That was Dr. Lukas Rickert, who hopes to inspire young scientists by letting his chip travel across the world. Good luck. Now, our fourth PhD finalist, has been preparing large entangled cluster states, the very basis for measurement-based quantum computing. He used and optimized emitter qubits in a cavity to achieve this, and he comes also from the Technical University of Munich. Please welcome warmly Dr. Philipp Thomas. Welcome, Philipp. Getting ready. All right.
Quantum entanglement is one of the phenomena that truly sets apart quantum physics from the classical world. On a simple level, you can compare this with a pair of dice that always kind of magically agree on a number they want to land on. But this is not the whole story. In fact, entanglement is one of the key resources for modern-day quantum technologies. But there's a problem. Entanglement is extremely fragile, especially when it involves many particles. Yet, on a large scale, entanglement is actually what you need in order to build, say, a powerful quantum computer. And on a large scale, it is also where this simple dice analogy fails. And in this respect, a very specific and very special type of entangled state is called the graph state. And what's unique about them is that these states can be expressed in a very compact notation in the form of these graphs, and they fully describe the entanglement properties. Now, in the context of quantum technologies, graph states can be understood as a sort of raw material that's used for certain tasks. Much like a piece of paper, a blank piece of paper, is the raw material for communicating via a letter. The problem is that unlike a piece of paper, graph states are very expensive to make. In fact, technologically, it's quite difficult to prepare a graph state that's large enough to become of practical use. Now, in my thesis, I have developed a method for preparing large graph states efficiently, consisting of photons. My team and I have used single atoms in an optical resonator, which essentially consists of these two mirrors facing each other. The atoms emit single photons, and they actually are stitched together by the atoms like beads on a string. Now, the cavity acts here as an echo chamber for light, which means they force the emission of the atom into a well-defined direction rather than letting them scatter into all directions randomly. And now if you repeatedly do this, you will get this cluster state or graph state that you can use in your protocols. Now my team and I have showed entanglement of up to 14 photons in this, with this method, which to this day is actually a world record. And this new approach could open up new possibilities, such as transmission of information over large distances, which is both robust against losses and secure. And this then could open up the way to large-scale quantum networks. Thank you.
Thank you very much. That was Dr. Philip Thomas. Congratulations on your world record. And finally, to conclude our pitches, we have a finalist who has realized a setup that measures vibrations below the shot noise limit. His thesis uses squeezed light to demonstrate applied quantum sensing in industrial environments. She comes from the Technical University of Clausthal. Please welcome warmly Dr. Mingwei Yu. All right.
Yes, ready.
And there's your 3 minutes.
Okay. Good afternoon, everyone. Today, I would like to introduce my work on a squeezed light enhanced laser Doppler vibrometer, or LDV. As you can see in this schematic, the LDV has a heterodyne interferometer and use this structure to measure vibrations. And they create a frequency difference between the measurement beam and the reference beam to get a carrier frequency. One of the main limit of today's LDV's sensitivity is short noise, and which arises from the random arrival of photons. And the way to improve this sensitivity is simply to increase the laser power. But that is not always possible. To measure some tiny structure or microscale structures. And then you can see the measurement beam must be so tightly focused down to 1 micron in size. And that means even 10 milliwatt laser power results in an extremely high power density, around 10 gigawatts per square meter. And this can hit the dampers and cause the thermal expansion or degrade the measurement sensitivity or occurrence and even damage the mass sample. So, to improve this sensitivity, but without increasing the laser power, we use the squeezed light, yes, quantum technology. And the squeezing can reduce the noise, the short noise in phase quadrature of the light. And then you can see over the time, the noise at 0 crossing point is decreased. And then that means the measurement of the light phase will be more precise. According to Heisenberg uncertainty principle, the noise in another quadrature, amplitude quadrature will be increased, but it doesn't matter, we care about only light phase, it carries our vibration signals. And this squared light source is developed by the Professor Hermann Schnabel's group at University of Hamburg. And I use this squeezed light. My LDV achieved 2.6 femtometer per root hertz. And this is in a demodulated displacement resolution. And this is a new record. For the comparison, the best industry LDV has 8 femtometer per root hertz. Thank you.
Was Dr. Mingwei Yu giving us insights into LDV, and also here a record set, so congrats for that. All right then, everybody, that was a veritable whirlwind of quantum here. And with this, we have heard of all 10 finalists. Please join me in giving them a huge applause for their exceptional work. And all this presented in 3 minutes with one slide only. It has been a very tough challenge. And it's going to be a very tough challenge for the jury. I see their eyes. It really is tough. That's the moment of truth. They will have a very difficult decision to make, and you may be too, because in the meantime, while the jury deliberates, it is your time to decide. Everybody here on site and you online. The online voting for the Audience Award will be open shortly. If you're watching the live stream, you will see the QR code, and if you're in the room, you will see it too. No worries. You have approximately 10 minutes to cast your vote for the pitch that you felt was most clear and most compelling and most communicative. And we will take all a short note and let the jury deliberate, and we'll see each other again refreshed and decided in about 10 minutes. See you then. Enjoy your break. All right, welcome back everyone online and on site. As you can see, the jury is back. She has decided, they have decided. I hope also you have all exercised your democratic right and have cast your vote for the audience award. The lines are of course closed now. And it is all about the second place winners and the first place winners. And I can see that the tension is rising, so we will not drag this out any longer. We will begin with the runners-up, so with the second place winners. And we will start with the masters. And for this, I hand over to Professor Dr. Martin Klicht.
Yeah, thank you, Helen. The second prize for the master thesis goes to Trevor Wozniak. Congratulations.
Please stay in the middle and enjoy what Professor Klicht has to say.
So I really enjoyed reading your thesis, and photonic crystals are, yeah, for me as a theorist, these are like magic small devices that can create entangled photons, and they have been existing for quite a while. And I was really impressed that within a master thesis you can still improve them, and I think that's a great achievement. Many congratulations.
Thank you.
And maybe Trevor, you'd like to say some quick words too.
Yes, big thank you to Sebastian, who's here today, Dennis Arslan as well, back at Fraunhofer IOF, Falk Eilenberger, Thomas Perch, everyone for the supervision and help during this whole thesis. I'm keep working in the same group for my PhD, so maybe I'll be back here in a few years. We'll see what else we can achieve. Yes, and then big thank you to all my friends and family watching in Jena, back in Canada, online, everywhere. Yes, thank you all.
Thank you very much, Trevor. Please stay with us for the time being. Maybe you can just come a little bit closer to me, and I will hand over for the second place winner in the PhD category. And for this, I ask you, Dr. Christian Main, to do the honors.
Okay. With a great pleasure to me for Marta Gilberte Basset for the second prize in the PhD thesis category.
Congratulations.
Congratulations.
Thank you.
Yeah, for me it was a great pleasure to read your thesis, and it is, when do you expect to have this one in an application, at least for, I think, medical things? Do you?
Well, we actually are in a project.
Maybe I can
Yes.
hand you this. Start from the scratch.
So we are actually having a project that is in that direction. Maybe not, it will not be the most compact device by then, but it finishes in 2 years. So hopefully by then we can have some medical images.
That's great. Thanks.
Thank you.
Thank you very much. Some final words from you?
Yes, I'm very honored to receive that, and I would like to thank all my colleagues in Jena and, yeah, of course, my family and friends. And, yeah, thank you.
Thank you very much. Congratulations. Could I ask you to step here for a while, but we need you. All right? Okay then, everybody. Now we will come to the first place winners, to those two on the very top. We will start with the master's thesis. Don't let anybody read this. Professor Dr. Anja Mitzelmann, and I will hand over to you to do the honors.
So, it was really a big pleasure to read all these master theses. I was very impressed. You know, I want to give them to my students as examples. But unfortunately, only one person can get the prize, and I think we found the right person. We optimized the process, and the first prize goes to Annelina Berlegina. Congratulations.
Congratulations, Adelina.
Oh, God.
Maybe I hold this for you and you grab the trophy, the crystal trophy.
Okay, thank you so much to the jury for this great honor. Really, I have to say a huge thanks to my former supervisors, Jeanette, Benedikt, and Frank, all my former colleagues at the Fraunhofer IKS, where I actually wrote this thesis. Shout out to you. Also, my current group at the University of Augsburg, QLab Augs, you're amazing. And finally, my family, friends, and mentors, some of whom are watching right now. Thanks for everything. You're the best.
Well, and you are the best. You stand right where you are, that's perfect. And you are the best, at least as the masters are concerned. And now, for the first place winner in the PhD category, I hand over to you, Dr. Peetz.
Thank you. So this, although it's obviously a difficult one, but this was quite an easy one, because after reading the thesis and after the presentations, all of us were completely convinced that we found the winner. Dr. Philip Thomas, please come up here. For you.
Thank you.
And shall we? Yeah.
Yes.
And my question is, how will you use the prize money?
That's a good question. I'd like to maybe do some kind of course to, learn something new. I still have to figure out what exactly, but I'm sure I'll find something.
Okay.
Yeah.
So keep getting better every day.
Yes.
A great applause. Maybe we can have all four of you in the middle. And here we have the second place winners and the first place winners, and a round of applause. And it's not over yet, because we, of course, have the Audience Award for the pitch that resonated most with our audience, both here in Berlin and wherever you all are. Maybe we could split in the middle, because we will see on the screen who won. I think we have a slide. Yes, and it is Trevor Vrchkovnik. A great applause. And it is really great that you have that you were born with two hands, because you have a lot to carry home. What are your feelings right now when you see that the whole audience has voted for you?
Yeah, thank you to everyone. I guess practice pays off, because I was up late last night practicing the pitch, so I guess it worked out. Yes, thank you to all my friends and family and the audience who was watching and decided to vote for me.
Well, it really did work out. Dr. Lucas Rickert also was close, and Dr. Marta Gilabert Basset was also there. So applause for all three. Very well done, and thank you for participating to the audience. So, what an exceptional afternoon. We really celebrated the very best of German quantum research, and we got to know and we got to meet the next generation of scientific leaders. And I would like to hand over to our host, Dr. Peetz, for the concluding words.
Thank you very much. So I don't have a lot to add, because we are here because of the young talents, and I think it will be interesting to follow your paths. I heard some of you are continuing with PhDs, so maybe we will see you here in a couple of years again. And I hope that you keep inspiring young students to follow your paths. So I think if we manage that, then we have managed a lot today.
Thank you very much, Dr. Peetz, and thank you, of course, to all 10 finalists. You are all winners. Dr. Peetz has mentioned this in the beginning. And thank you, everybody, for watching, of course, and thanks to the Ministry of Research, Technology and Space for initiating and for hosting us, of course, the brilliant jury for their deliberation, and to the VDI Technologiezentrum for the flawless organization. So everybody, thanks a lot. You've made this event really worthwhile. And if I can say, have a great afternoon, have an excellent day, and keep looking to the quantum future. Thanks. And everybody here present who would like photos, all right? The stream is over, but now is the big